Okay, everybody, here we are for session 5, Tire-Derived Aggregate Research and Applications. Hope you guys all like that little dessert. I did. At this point, I'm going to turn it over to one of my teammates here, Matt Weiss, to talk, waste management engineer with CalRecycle, and he's going to moderate this session. So take it away, Matt.
Thank you, Kyle. Hello, everyone. Welcome to Session 5, Tire-Derived Aggregate Research and Applications. I'm Matt Weiss, and I serve as a waste management engineer in the Tire Engineering and Environmental Research Unit at CalRecycle, and I'll be the moderator for the session. The session is being recorded and will be made available to watch after the event. As a reminder for our virtual audience, you can ask questions during the session via the Q&A widget. Please note the speaker's name, then your question if it applies to a particular speaker. The Q&A will be at the end of the session after everyone has presented if time allows. Our speakers today will be Dr. John McCartney, professor in the Department of Structural Engineering at the University of California, San Diego, specializing in geotechnical and geoenvironmental engineering. He will be presenting on his recently completed CalRecycle-sponsored research on tire-derived aggregate, bearing capacity, and seismic mitigation. Then we'll have Dan Goods, the contract manager for the Metro Gold Line Foothill Extension Construction Authority. He will be speaking as a past CalRecycle TDA grant recipient and will share his recent success on TDA used as vibration attenuation under light rail lines in the Los Angeles Transit Metro line extension. And then finally, we'll have Chris Doolittle, a certified engineering geologist with the County of Santa Barbara Public Works Department, working in the transportation engineering section. Chris will also be speaking as a past CalRecycle TDA grantee and will share his success on using mechanically stabilized TDA used as roadway embankment fill and repair for the Ortega Ridge Road project. Detailed bios of each of today's speakers can be found on the online agenda on the Tire Conference website. And now I will hand it over to Dr. John McCartney to start the presentation.
Thanks, Matt, for the nice introduction. I'm very happy to be here with you remotely. I'm sorry that I can't be there in person. I'm on sabbatical in Croatia, so it was a little bit of a far trip to come for the conference, but hopefully I'll be able to meet you at the next one next year. So today in my presentation, I'm going to tell you a little bit about some of the results that we obtained from a recently completed project here at UC San Diego. That's basically geared towards understanding the engineering behavior of the foundations for structures that are installed in TDA. You'll hear a little bit in the other presentations today about applications of TDA as a lightweight backfill in civil engineering applications. These pictures that I'm showing here are actually from the Ortega Ridge project that you'll hear more about in one of the later presentations. But one of the challenges that we wanted to address through this research project was to understand the behavior of foundations that would be installed within this tire-derived aggregate. I'll talk a little bit about what sort of structures would be installed in the TDA in a second. But before I go through some of the detailed results from our testing program, I'll tell you a little bit about TDA material properties and how we can use those material properties together with some theories to predict the behavior of the foundations. Then I'll go through some details of our bearing capacity testing program. This is basically how much can you load your foundation installed in the TDA, and then a seismic response testing program to understand how a foundation would behave if the ground was shaking below the TDA layer. So the project had two phases, as I mentioned. The first is where we looked at the load settlement response of footings installed within the TDA. We did 8 different experiments where we changed the width of the concrete footing, the shape of the footing, the angle of our load. But in all of these cases, the foundation is going to push down into the TDA, and at some point it's either going to tilt sideways or reach a capacity value. And then we want to take the measurements that we had from those experiments and compare them with some theories that geotechnical engineers use to predict the bearing capacity of foundations in soils. We want to see if those apply also to TDA. Our second phase, we wanted to look at the seismic response of the footings in TDA. So this is a very interesting future application. I think that this has a lot of potential for TDA. TDA is used as a vibration isolation layer in railways right now, but maybe we can also use this as a way to mitigate the effects of earthquakes on structures by providing a low-cost seismic isolation system. We have seismic isolation systems that we can buy from companies that are on the order of hundreds of thousands of dollars. So if we're able to use this recycled lightweight TDA, it's a very low cost for, as we'll see, almost comparable performance. So why do we want to study the bearing capacity of footings in TDA? We use this as an alternative recycled lightweight backfill. And in many cases, we need to install systems like signposts or guardrails. These are very lightweight systems, but also thrust blocks for utilities. So when water goes through a pipe, it's going to create a thrust, and we need to make sure that there's adequate support for that. And engineers have worried, okay, well, what should we do when we're trying to figure out the capacity of these systems? And there really hasn't been any guidance at all in the literature on how to do this. And guardrails, signposts, those are all very important. You don't want this to sink down into the TDA. We need to have a good experimental basis to justify any bearing capacity values that we decide to use. TDA can also be used as a bridging material. So if you apply loads through the TDA, you could have a stress reduction on a buried pipeline or other utility system. And our research on the bearing capacity could also be applied towards understanding the bridging materials. This is just a schematic of a MS TDA wall that we'll hear a little bit about later. Another interesting thing on why we want to study the seismic response of footings in TDA. If we have a shallow footing on soil and we design the footing to be very large so that it would have a very high bearing capacity, one challenge during the earthquake is that the energy could be pushed from the ground into the structure, and you could end up having a failure within the concrete structure. This is just a simple model scale experiment on the right showing a large conventional capacity designed footing with a structure on top of it, and then another footing that is allowed to tilt and rock during an earthquake. So if you allow your footing to be a little bit smaller than you would want from your static bearing capacity design, but still stable, when the earthquake happens, it's able to tilt and rock and dissipate energy and come back and recenter itself after the earthquake. So this was something that we wanted to study. People have looked at these rocking foundations on soils, but there are still a lack of tools to control the behavior of these rocking foundations. So if we can use TDA beneath this rocking footing, we may be able to gain even better response than people have seen in the past. So this was something that I'll show some actual experiments on TDA and instead of on sand, as you can see here. So before we go into, talking about our experimental program, I just wanted to give you a little bit of background on TDA and some of its properties that we've measured in previous projects sponsored by CalRecycle. We're focused on type B TDA. So this is TDA with large particle sizes up to 1 foot in 1 dimension. This has lower processing cost, less exposed steel, and because of those, you can use thicker layers up to 3 meters or 10 feet. And that's advantageous in our geotechnical applications. Whenever you have big particles, you need to have big testing devices. So one of our early projects was to develop a large direct shear box to measure the shear strength properties. Once we did this, we found that the properties of the TDA are very similar to those of soil, but with the main exception that it takes a lot of movement before you can reach the strength of the soil. So the strength is where this curve reaches its peak. You're almost getting a half meter of displacement before you get to the peak. So there's good things about that. It's a very strong material, but it's very flexible. So these are just some different failure envelopes that are telling you what the strength at failure is versus how much load is on the TDA. And our goal was to take the parameters of these failure envelopes that we developed in a previous study. It gives us something called the friction angle. And we're going to want to see if we put that friction angle into some predictive designs, is it going to be able to give us the same bearing capacity that we're measuring? We've also done some compression analyses. One important thing is when you load your footing, it's also going to settle a lot. These curves here are showing basically that TDA is expected to settle more than most soils. Soils have a value of this parameter that's maybe 10 times smaller than that of TDA. So we can account for that in design by using more TDA in the layer so that once it does settle, it comes to the desired height. Okay, now onto our bearing capacity testing program. We repurposed some large concrete blocks that we had in our lab to create a big box that was basically 10 foot by 18 foot in length. And we were able to put 10 feet or 3 meters of TDA within that. You can see a person sitting here for scale. And then we had a loading frame, and we could apply loads through a hydraulic actuator to a footing. This is just a picture of the TDA that's been installed into the box, and we used a bobcat to compact it into place. It's not the same as you do in the field, but it's as good as we could get. We did some early tests where before we had all of the TDA that we needed to fill the box, where we just squished the TDA and made some comparisons with our previous direct shear test measurements, and we saw that we could get a very nice hyperbolic curve to represent the load settlement response. Here's a summary of the 8 tests that we did. We varied the embedment depth, the size of the footing, the shape of the footing, and then the angle of loading. Those are all different things that you may encounter in different projects. These are some different pictures of the different footings. You can see it's a strip footing for most of the cases that we looked at. It was on the surface, it was embedded into the TDA, a wider footing, cylindrical footings that you may encounter for those signposts or guardrails, and then inclined loading, where we applied loads at different angles. These are some of the different curves that we obtained from our tests. I'm not going to go through the details in explaining the differences between all of these. It kind of followed the logical trends. If it's a larger footing, it's going to be stiffer. Smaller footings are going to be softer. But one thing that you can notice is that there's a very large amount of settlement that we can obtain in these tests. Our footings that we tested were ranging in size from 1.5 feet in width to 3 foot. So if you're getting 1.3 normalized settlement, that's 1.3 times the width, 1.5 to 3 feet. That's a lot of settlement compared to soils. So we did reach bearing capacity failure in many of those cases, but it may not be good from an engineering perspective to go all the way out to bearing capacity. We may want to define a settlement criteria like these dots up here that says we can define failure at the point where you've reached 10% of your footing width. So I'll talk about that here on the next slide. So the first thing we did is we took that friction angle from our direct shear tests that we performed on the TDA itself, and we plugged that into a very commonly used bearing capacity equation. This is Brink-Hansen. This gives you the ultimate bearing capacity, the maximum load that you can apply onto the footing before it tilts and falls over. And we compared that versus the predicted values on the x-axis. We compared that with our measured values from the experiments. And the first thing we did is we compared the points where we were at the excess tilting. In all except for one, we had a very good match. But the main thing I mentioned on the previous slide is that large settlements occur when we get to that tilting failure. So even though we had a good match between the theory and our experiments, that's not really very practical. So we came up with a new equation that correlated the predicted value with the bearing capacity at 10% of the footing width. And we can use this correlation in design, give us a bearing capacity that is also going to lead to small settlements. Okay, so that's kind of it on the brief overview of the static bearing capacity tests. So now moving on to the seismic testing that we performed on the footings in TDA. We have multiple different shake tables at UCSD. If you're interested to come visit, there's a lot of cool facilities there. We used our medium-sized table in the Powell laboratory that can accommodate this large laminar container. It's about 3 meters tall as well, about 4 meters wide and 1.5 meters wide. And we can fill that with TDA to different depths and put a footing into it in a configuration that you can see like this. We did 3 tests with different layer thicknesses and different A over AC values. This is basically if you decrease the width of your footing, like I showed in that early video, your area is going to be getting smaller. And depending on the characteristics of your mass, you're going to have a critical ratio at which overturning is going to be expected. So if you look at that ratio, it's basically another way to look at the factor of safety. A smaller value is more dangerous and a large value is safer. So I'm going to show you the results of this bottom test here, which had the lowest value of A over AC. And we shake it in this direction, and there's basically a lollipop that is rocking back and forth on top of the TDA layer. So again, we had our container, we filled it with TDA. We had one of the footings from the previous test and put it into the TDA layer and filled it up to the top of the footing, and then had this stack of weights on top of here that's representing our structure. And I'll show a video on this slide. This may be, hopefully it's not too loud. The main thing you can notice from that test is that the footing comes back, the mass comes back to where it was at the beginning of the test, which is very good. That's kind of an indication of good recentering. You can see that there was not really any more settlement during the shaking event. When we first load TDA, we can expect some, relatively large amounts of settlement, but after that, it's going to be relatively stable. And we don't see a large amount of settlement during shaking. And our results also indicate that there's a large amount of energy dissipation. So that means that the energy from the earthquake is being dissipated in this rocking mechanism, and it's not causing failure within the structure. So that's what's kind of being shown on some of these plots here. We see these are the blue, black, and green are soil rocking foundation tests. The red is our TDA. It has lower amounts of settlement than all of these other cases, although we do have a little bit more rotation. So that's an issue. You saw the mass was moving a little bit more back and forth. The damping ratios for the system are relatively similar, but there's an increasing trend. So the more rocking that you have, the more energy is being dissipated. We can also look at the loops of the stress versus strain and come up with some different ratios. I won't go into a lot of detail here, but the bigger the size of this loop, the more energy is being dissipated, which is good from protecting the overlying superstructure. And we have a recentering thing, which is telling you how well do you come back to center. So one good thing is if we compare these results from soils in the triangle and our TDA in red up here, we have very, very good recentering. We're almost perfect recentering. And this plot on the right is showing that we again have very good recentering, but also pretty good energy dissipation. In the soils, you need to have some amount of poor recentering in order to have energy dissipation. But that's not the case in the TDA, which is a very positive sign. So I have about a minute. So in our bearing capacity tests, we found that there were relatively large settlements by the time that we were able to get to our bearing capacity. But one nice thing is that we had a good match between our experimental results and our theoretical bearing capacity predictions. The only issue is that large settlements are needed to reach the failure criterion. So we came up with a design equation that can be used so you can know what the bearing capacity is while not having a large amount of settlement. And I think hopefully from that video, you can see that TDA has good potential for providing geotechnical seismic isolation, as long as you're able to accommodate the rotations that could potentially happen in the superstructure, or maybe add some additional features into the TDA, such as reinforcement to help control the amount of rotations that you obtain. So with that, I'd like to acknowledge the students and collaborators that I've had on this project. I'm very grateful to work with CalRecycle and Joaquin Wright at GHD. They've been very critical in helping to for these projects to come to fruition. And we have great lab staff and great students that do all the hard work and get pricked by TDA and particles all the time. Although once you get pricked, you don't get pricked anymore. You learn. So with that, if you're interested in learning more, you're welcome to email me. And there's some details of a couple of our papers on this topic. So thank you very much for your attention, and look forward to questions later.
Thank you, Dr. McCartney. As a reminder, once again, we will wait till the end of the presentations for questions and answers. So moving on, we have Dan Goods.
All right, thank you, Matt. All right, try to work this. So my name is Dan Goods. I'm the contract manager for the Metro Gold Line Foothill Extension Construction Authority. So what are we? We are a state, we're not LA Metro. We are a state agency created under an assembly bill back in 1998 to build what is now the northern leg of the Metro A line, what at the time was the Metro Gold Line from Union Station initially to Pasadena. Then under a separate state assembly bill in 2011, the authority's charge was expanded to extend that line. So we've extended between 2012 and 2016, we extended the line from its original terminus in Pasadena to the Azusa-Glendora border, and we are currently constructing what is we call Phase 2B from Glendora through San Dimas, Laverne, and Pomona. And we are in the process of securing funding for a further extension from its current planned terminus in Pomona through the remainder of Pomona, Claremont, and then across the county line to Montclair in San Bernardino County. So let me go back here. So the segment we're currently building, Phase 2B, is about 9.1 miles. Of that, so it's double-track light rail. We're building on a right-of-way that is occupied by a freight line. So we've moved the freight line from the middle of the right-of-way, either north or south, to the edge of the right-of-way, and in the vacant space, we plop 2 light rail tracks. So all of that said and done, we're building just shy of 100,000 track feet of light rail. And during the environmental phase, we identified 28, almost 29,000 square feet, which needed vibration mitigation because we're putting a track closer to a sensitive receptor. Most of that is residential and a little bit of commercial space where we'll have increased vibration from trains being closer to them. So of that, there was one area that we have to install a floating slab, which I'll get into what that is in a minute, where we had a vertical and a horizontal curve next to an existing bridge that we do not want to touch. So we have to put in a floating slab for about 200 track feet, which is a big old expensive pain. And the rest of it, we are allowing our design build contractor, we allowed our design build contractor to choose whether they could install ballast mat or tire-derived aggregate. There are a few places where we had to install 2 layers of ballast mat, so I have to go with that. But the remainder, you either install 1 layer of 1-inch ballast mat or a foot of tire-derived aggregate, and every opportunity they were allowed to make a choice, the contractor chose to install the TDA. So that tells us a lot about the overall cost of the system. So a floating slab, mentioned this is a big old expensive pain, because what is it? It is really, you're building a trough within a trough. So you have a reinforced concrete trough. I apologize for this graphic. This was the best cross-section I had, but it is a reinforced concrete trough with a layer of vibration attenuation. So it's basically 3 layers of ballast mat, and then another reinforced concrete trough built inside of that, which then we have to put our sub-ballast, ballast, rail, everything on top of. So it's a lot of extra excavation, a lot of steel, a lot of concrete, and we all want to avoid that. It does offer superior noise and vibration mitigation, but it's about somewhere between 10 and 14 times as expensive to build this as to install just a ballast mat. So, ballast mat is a rubberized polymer mat we place under our sub-ballast, and it is the material itself is more expensive than TDA. It requires on the surface less labor to install it. You buy these mats, you roll them out, but it is delicate. You're putting, generally we are between 20 and 25 feet of width underneath our tracks, per track. So you have several layers of this ballast mat you have to roll out, and until you get your sub-ballast placed on top of it, it can tear, it can shift. If your contractors, crews are not careful, you have to basically rip everything up, start over again, and that is one of the main reasons that our contractor chose to install TDA, which, again, a horizontal project like we're building is about the perfect use case for tire-derived aggregate. You can see this cross-section. It's basically it's this blue highlighted area right on top of our subgrade, below our subballast. So we have a little bit of extra excavation, put down a layer of geosynthetic fabric, roll your TDA out, wrap it up like a burrito, proceed with your construction. So we'll get into this here in a moment. The noise and vibration isolation potential of this cross-section is nominally equal to a 1-inch layer of ballast mat. So how does this look in practice? And luckily for us, our contractor's done this before. We've done this before. We did this on our Phase 2A, our Pasadena to Azusa phase. So agency had practice with installation. The contractor had practice with installation. So we go in and as they're excavating, basically excavate slightly deeper, dig a trench out. You can see here the second photo, installation of the geofabric. And you bring your trucks in, drive them right through your trench, open them up, dump your TDA out, pull it out, consolidate by rolling half a dozen times. I think our contractor always threw a seventh in there for good luck. Just roll over it, consolidate your TDA. As they're pushing it along, you get your good layer in there. You can see in the second picture here that, once it's in, you're not going to do too much with it. We're using type A TDA, which is a smaller particle size than Dr. McCartney was using in his research. So it's nominally, I think it's about a 200 millimeter is the largest diameter or largest dimension of your TDA, type A. So once it's consolidated, it's really not going anywhere. It is just place, wrap it up just like a burrito, and then we install subgrade right over top. You can never tell it was there, and once your subgrade is in, it is pretty much bulletproof there. Even before you have the subgrade in, other than tearing your geofabric, there's no real installation issues. So our contractor likes it. We heard very positive feedback during industry review when we were in procurement for this contract back in 2018. When we did our industry review panels, we asked the contracting community if they would like to use it because it was we like to tout it as a big sustainability feature of what we're doing. So very positive feedback. Our contractor, used it everywhere they could. This is a breakdown of all the different areas we used it, and we totaled out just under 5,500 tons of TDA. It's about 100 tires per ton. So we overall utilized about just about 0.8% of the 60 million tires that are annually generated as waste tires in this state. So like I said, it's a pretty good use case. We were able to, contractor likes it because they can work very efficiently. That operation that I walked you through, it's about 2 shifts to get it installed, installed, consolidated, wrapped, and get sub-ballast laid. So it overall amounts to about an extra 10 to 12 crew hours to install that. So we've had great success with it. It's something that we'll continue as we go into our next phase of procurement to look into, allowing everywhere we can. So that is the end of my presentation. Be around for any questions later. Thank you.
Thank you, Dan. And last but not least, we have Chris Doolittle to finish us off.
Okay. Thank you very much for inviting me to speak with you today. And talk about a project that's near and dear to my heart. I've been working at the County of Santa Barbara for close to 27 years. And when I started, it was just as a soils tech, doing a drill rig. We actually went to this site and drilled down to try to figure out what the problem was, and that was like 26 years ago. And we finally got this problem mitigated in 2019, after many different attempts, and I can go through the various attempts that we went over, but we're going to go through this project, and knowing that we just got a pretty good presentation on TDA, I'll try to skip most of the TDA, related stuff, but we'll talk more about how the system as a whole integrates with the TDA and the various geosynthetic materials, which are, as we've seen, are a very big component of installing these, is keeping the materials separated from the natural environment and other materials that are there. So we did submit this project for the League of California Cities and CAC, which is County Engineers Association of California, and the CSAC. So it did get a substantial recognition as the Outstanding Local Streets and Roads Project overall winner back in 2020 when we brought this forth. We thought it was a very innovative project, and we're happy to work with our partners at CalRecycle and GHD on the development and in construction and continued monitoring of this project. So what is an MSTDA wall, right? It is basically same thing as a mechanically stabilized earth wall, which you're basically using geosynthetic elements and a retention element on the face in order to retain a large embankment. In this case, we are just substituting out the earth component for the TDA. And why we use the TDA was primarily because of the abilities that it does generate, which is it's a lightweight fill. Now, there are other lightweight fills out there that you can utilize, but this TDA is substantially less costly than the other alternatives that we would potentially use in this case. So MSE wall, we just talked about that as basically a geosynthetic reinforcement within the wall. And in this case, we use two different types of geosynthetics for the stability of the wall, which is uniaxial, which is providing basically one directional force resistance and tensile strength. And then we use the biaxial geogrid more for overall stability and settlement mitigation as we get more towards the surface of this installation. And as you see here on the bottom, TDA, we use type B TDA, which is the larger lengths, 4 to 12 inch typically is what we would see there. But yes, it's a low density material. It's got great permeability because it has so much air voids within it. It has a high friction value. So once it has force applied to it, it has a high friction value for movement, and it's lower cost. So a little bit about the project site here. This was in the town of Summerlin, which is in the county of Santa Barbara, and it's right along the coast. As you can see here, the area of Summerlin itself is sort of like a ridge amongst all the remainder valleys. So it's sort of a high point geographic feature, and we'll go into a little bit more about the site in the next photo, but just generally kind of getting you located in the state of California for us. This is an overall picture of the project site. And as you can see, there's sort of a developed drainage on both sides. So this was like a notch in the ridge line. And so it's a normal drainage area. Surrounding farmlands and residential street, it's sort of a cutover roadway from Montecito to the backside of Summerland. We wouldn't consider it a high capacity roadway, but we'll get into its uses in just a little bit. So a little bit about the history of this site. I am going to preface, I am an engineering geologist, so we are going to see an engineering geologic map in a second. This roadway was originally constructed in the 50s. At that time, they basically were trying to fill in that notch in the natural drainage, right? So they ended up bringing in about 23 feet of fill, just locally generated materials from the 50s, just cut fill, and just put it in the hole and brought it up. But, compared to modern construction techniques, the techniques used back then were not that great. The type of materials they had, the type of equipment they used, the effort they used to compact these, and definitely the materials that were used, the soil itself was substandard. So they tried to address some of this, by putting in the 70s, they had some issues with it, that they tried to put in a culvert to, continue the drainage through there, but we ran it. There's some problems with this. And you can see here in the lower left, kind of the original road alignment before they filled this in, pre-1950s, was the road actually went down along the drainage and back up. So here's the map. So I will tell you a little bit about the soils here. The soils they used were locally generated, and it's the Rincon Shale. Rincon Shale is a very problematic soil. It is highly expansive material, which in this case means like when it gets wet, it expands up quite a bit, and then as the dry season comes every summer, it will contract. And so that, excuse me, that leads to differential settlement of the soil. So what that means on the roadway surface is you're going to get this creep, right? The embankment and all the support soils are just basically creeping every summer. They raise up and then creep down, with the gravity. So we ended up having kind of a lot of issues at this particular site. These are the conditions that we experienced in 2015, and this is after several decades of them trying to address this problem. You can see the large amount of settlement cracking that's throughout the site, all pretty much linear, right? It's all along the same, dimension as the roadway, with the downslope edge of the roadway continuing to settle at a faster rate than upslope. So what this ends up doing is maintenance crews have to go out there and have to deal with this all the time, right? So what do? They just put on another layer of asphalt, right? They just try to smooth the road out, right, for the traveling public. So when we were out there investigating, we ended up seeing that there was over 30 inches of asphalt at the edge of this roadway. So they've been doing this for a long time, just continuing. So every layer of asphalt they put on there is more weight that then is going down and compressing these soils on every time that this, it's just a repeating cycle, getting worse and worse and worse. So in November of 2015, it finally reached a breaking point. It was getting so bad that there was massive differential settlement. We had like 4 inches of settlement within the travel lane. And so it wasn't like a landslide that was really, just a massive event. It just was continuing to devolve. And so in November 2015, it got so bad that people were, understandably concerned. And so we went out there as a stopgate measure to go ahead and basically create new shoulder width and move part of the roadway over. And then we had to close off the lane because everybody thought it was going to just collapse, and or other was going to create another driving hazard. So we went through that towards the end of 2015, and then we got serious about doing a permanent repair. So in working with CalRecycle and GHD, that were supplied to us some good technical knowledge on some new techniques that were going to be, that are being used throughout the country, but hadn't yet been used in California, which is this MS-TDA wall. So we went through a geotechnical investigation design. I won't get into too many details, but one of the things we want to highlight is the existing conditions out there was that this material, this Rincon Shale, was basically oversaturated. It was not very well compacted. It only had 78 to 84% compaction, where normally we'd be seeing 90 to 95 is what we would be looking for underneath there. and it retained a lot of moisture. The existing soils were 25 to 39% moisture content, which is basically turning it into a real pliable and compressible material. Due to the high void ratios in there from this action, it was just anticipated that this settlement was just going to continue or even get worse over time. The initial recommendations, as they always are just over-excavate 3 feet down and try to put in some superficial reinforcement and then repave the road. But we went forward with this, and so we did some modeling of this and used some of the information that's been supplied through these laboratory testing programs that have been in place with CalRecycle and some of these universities to develop this technique. So we have some geotechnical data, and then we can just put it right into a normal slope stability model like we would for a soil. So that's what we're seeing here, is we are just modeling the TDA as if it's a soil component, right? We give it a friction angle, we give it a density, and then just utilize it in your normal slope stability. For these things, we need to get a long-term static factor safety of 1.5, which we were able to meet here, as well as the pseudostatic for the earthquake. It's able to meet that through this modeling. What you will see on here is that there's a lot of reinforcement in here, geosynthetic reinforcement. So I'll try to skip through these mostly, but just want to let you know that this is something that you can replicate, model, and using the available data, you can do the same work as a traditional geotechnical investigation and design. So eventually we came up with a pretty hefty design, and it was going to go down pretty significantly deep in order to replace enough material so that we could get, for one, down below the area of disturbance, but also generate deep enough and wide enough area that we could use a substantial amount of TDA and make it kind of more of a cost beneficial analysis and be able to, utilize some of this tire-derived aggregate that's available. So in terms of the actual design over here, what we do is when we excavate down, we brought in some engineering fill at the bottom, stabilized the bottom there, brought in some geosynthetics, like we've heard these before, a burrito wrap, right? It's a geosynthetic material that you use to keep the rest of the soil out of the TDA zone. And then we had a pretty substantial here TDA zone. I think it's about 9 to 12 feet thick of TDA. And you can see the retention elements on the side. This is a welded wire basket retaining wall system on the side, and then the geosynthetics with the uniaxial grid moving into the TDA, so we can just go ahead and put those right in. So I'll get into construction photos in a second, but we got this all ready to go in late 2017, and we're just about to advertise this project in early 2018 when we had a monumental event in Santa Barbara County. It was the Thomas Fire debris flow, January 9th, which basically devastated the whole area around Summerlin, Montecito, Carpinteria, and the area. So it was a pretty monumental event. Besides taking away, staff, it also basically took away a lot of the access to the whole area. So this is a map. You probably can't see it that well, but you can see by the number of dots on there that there was a lot of damage. Mainly what I'm highlighting here are bridges over creeks that were damaged. So we had several structures that were completely lost, as well as several structures that had rails that were completely blown out. So a lot of the bridges had to be replaced or otherwise fortified. And this road that was now down to one lane ended up being the only road that was able to transmit traffic, and especially large hauling of all the debris out of our debris basins, which is millions of truckloads worth of debris that had to be transported out. So we had to keep this thing open in suboptimal conditions until all the debris could be removed and pulled out of all those places, because it was really the only road that was able to access these back sections of Montecito. So finally, the last debris basin was cleaned out, and we were given the green light to go forward with our project. So we advertised it, and got some bids. We actually had quite a bit, and we'll go into that later but we had quite a lot of interest in this project. You know, a lot of them were maybe hesitant about the use of TDA. They'd never worked with it before, but we just kept assuring them, just treat it like dirt. There's a couple things that are different, but just, it's a material, use it, and we'll move forward. So here's the big excavation down. I think it's about 12 to 15 feet at the highest. And you'll see that ridge on the left side of the photo was really, we had to keep open a utility corridor. We were able to move some of the utilities out of the way, like we were able to move the gas line out of the way and arrange some of the other utilities to move out. But we did have a water line that had to remain in service. So that's kind of where we have that steep back wall. As we go forward, we're just going to go right through the construction sequence so you can see how this is utilized. So this is the first layer of the MSE wall, which is the welded wire facing and being placed on the engineered fill prior to the placement of the TDA sequence. And here we are, they're starting to roll out the fabric for the TDA to go on, and you can see some of the geogrid there on the left side. That's the connection to the retaining wall. And then finally, it was time for the TDA to arrive. So if you don't know, these TDAs arrive in massive trucks with moving beds. You know, areas and access are an issue, but eventually what every contractor wants to do is just have it delivered right to the site, gaining the quickest access. So, but that can be problematic sometimes because these are big vehicles, right? So the contractor, we leave it up to them to figure out how to do this, and they try several different methods until they can figure it out. So in this case, what we do want to mention that separation of the materials is key, right? You don't want to just mix this all in with the rest of your soils or your other construction materials, but eventually, you know, we can get it all in the right space. So here we go when they actually have the TDA and they bring it in basically in like 18-inch lifts usually, and then we kind of compact it. And it's a method compaction system. So you just go over with a steel, either like a dozer, a steel tracked, or a steel roller, and you just roll over it, basically 6 passes total, right? 3 in each direction with this material. Rubber tires, definitely not a good thing to have on your equipment. You have to have steel tracked equipment because the steel threads in the TDA will really foul up the equipment. Rubber tires equipment will pop the tires and everything else. And, you know, there's some issues with it in terms of the contractor learning how to work with it and use the right equipment. But once they get it, they just use it as a normal material. And so then, you know, as we're getting close to the wall face, you have to use lighter type of equipment. So we have mini X's and mini rollers to work within the 5 feet of the retaining surface so you don't overload those systems before they're all tied together. Once construction starts on a project like this, there's multiple operations going on at the same time because you have multiple materials that need to be utilized. You know, you have your welded wire people that are pulling that together. You're bringing in the rock to backfill those gabions or the welded wire. And then you have the TDA that's coming in at the same time, and then you have your geosynthetics as well. So all of this is kind of coordinated, and the contractor's trying to figure it out at the same time. But eventually we get to the top. So this is the top of the TDA, and we start rolling out the geotextile, which is the separation. And then from that point, we can start really moving. In this case, you know, we're continuing the welded wire facing all the way up, you know, beyond the embankment slope. So we're, you know, bringing in that material and continuing to progress the work. And we did use quite a substantial lot of material on top of the TDA. In this case, we used about 3 feet of engineered fill, which was reinforced by the biaxial geogrid. And then we got into our structure section above that, which was about 1.5 feet thick. So we put a lot of extra weight on there. We did talk about that there's a lot of settlement to this. So in some ways, you know, having more like fill, you know, operations is allowing more time for those materials to settle as you're continuing to struct and bringing it up the slope. So eventually we get to the top and laying out our biaxial geogrid for our roadway section. And putting in our final lift here of our wall and the rock. You can see the rock there as we're bringing that up. And pretty soon, project is completed. That's the way it looks like. Nobody ever knows that we have all this shredded tires underneath. And then it turns out just to look like a normal roadway. So I'll just go quickly through this because I know I'm out of time. Just a couple photos here of just showing the overall project scope, and just let you know just some of the contract information. We did get some funding from CalRecycle for this. We were part of a pilot project program for this, so we did get some normal TDA grant funds, about $100,000, and we were able to get about $330,000 of additional pilot project funds in order to build this. So the county on this case was only responsible for about $235,000 of the construction costs. We did use about 851 tons of this TDA, which in the approximation is about 80,000 tires. Now, the number I've been hearing today is 60 million tires a year. So in retrospect, not a lot, but for us, it felt like quite a big contribution. We were able to get the material for about $68 a ton, but the cost to implement and construct and haul and everything else was about $140 a ton is what the county was charged for that. So besides that, just here's my contact information. We've used TDA on a couple projects now, so if you do have any questions, I'm definitely available, and just definitely want to thank GHD and CalRecycle for their partnership and providing for a good project. It is got some load cells in it. It's got some other survey. So they're looking at it as a long-term study project to determine, what is the settlement, what is the load in there, what is the heat generation. So they're using it to continue to study to, put these out there for future projects. So with that, thank you very much. Appreciate your time.
Alrighty, thanks, Chris. We will now start the Q&A portion of the session. For our virtual audience, if you haven't done so already, please enter your questions using the Q&A widget, and we'll go ahead and start with our in-person Q&A. One sec.
Just curious, when was the completion date of that?
I think it was in late 2018 or 2019, I think was the actual construction.
And then the next question will be, so far so good? I mean, you guys liking what you're seeing and everything like that?
Yeah, it's been very stable. The main thing for us was to obviously get rid of the problem that had been there for decades. And so this was a good solution to that, especially with the lateral reinforcement of the welded wire, providing that support. So yeah, we've been happy. There's bound to be some settlement. We tried to alleviate that during the construction by, having periods of time where it was open and being rolled on by, the construction equipment. And we even brought it up to subgrade level and then just left it open to the public for a few weeks, just to let the additional vehicles run over there and allow it to have additional time to settle before we put on our final asphalt pavement surface.
That's very smart, letting the general cars go over it just to get some more compaction. So far so good, huh? That's
Definitely.
very promising.
Is John still key? Dr. McCartney, are you still on?
Yeah, I'm here.
Hey, this is Joaquin, right? The question I have is when we're looking at seismic isolation, and I know that you look at lots of different methods, how would we envision building a structure on TDA to get those seismic benefits?
So it'd probably have to be new construction. And you'd basically use the same techniques that we were seeing here, have the burrito wrap TDA layer, and then you build your foundation on top of it. And we're still processing our data with numerical models to understand the role of the height of the TDA layer. But potentially we could go up to the full 10 feet of TDA that's allowed in the ASTM guidelines if necessary. But the more TDA you're going to have, the more energy dissipation you're going to have beneath your footing.
Thank you, John. Any other questions?
Yep. So my question is for Dan. For the railroad project, do you have the data for like when you use the tire aggregate versus just a conventional way? How much is the difference in terms of like sound or vibration?
So we're using it primarily for vibration mitigation. For sound mitigation, we have a variety of sound walls. In a few cases, we have to replace windows or install air conditioning, or even, I don't think we've actually ever had to replace a roof, but we have criteria for that. So we're using it mainly for vibration isolation. And if you like, I can get you my contact info, and I can connect you with our noise and vibration engineers. But yeah, as I understand it, it is nominally the same level of vibration isolation for between a 1 foot lift of type A TDA and a 1 inch ballast mat. So that's how we set our contract up. Our contractor was allowed to choose, in those areas. It was about 5 total miles of area where they could choose one or the other.
I'm curious to know on the compaction on the TDA, is it known, like for X amount of feet, how much settlement you might get? Is there any formulas out there that can direct people or to guide, construction of these type of projects?
Well, no. I mean, what we're looking at is just the kind of a method compaction. And then for us, we put on a significant amount of cover material, right, that we can then evaluate and get grading on. But there is definitely potential for it to settle for, a couple inches during construction. But I think like time, right? If you can keep it in the ground and get it compacted and have time for it to come across to that. But yeah, that's a concern, right? It's a concern of, for a structure that you're going to put on there that needs a tight, tight compliance with grading, right? So in our case, it's really, we're just looking at the asphalt surface needs to be continuous and not settle.
And I don't know if you're concerned about rail. I mean, we're a bit of a more specific use case, but we have so much additional weight on top of, where our TDA is compared to a normal roadway. We've got, 18 inches to 2 feet of sub-ballast, and then, at least 12 inches of ballast, then, ties and rail and everything above that. So by the time we get to, when our contractors are done laying their sub-ballast layer, that's what they're tying to their surveyed, and then their engineered grades. So, and we haven't noticed, even the project we did from 2012 to 2016, there hasn't been any additional settlement of that section of that rail line versus what would be expected with any of the other light rail lines in the greater Los Angeles area.
Yeah, and sorry if I could jump in too. There are some good formulas and charts that were developed by Dana Humphrey. He was one of the pioneers on using TDA. And it's a pretty practical chart where you can, if you know how much granular fill you're going to have on top of the layer, it'll tell you how much additional TDA to put into there so that when you apply that granular layer, it's all going to come to the final grade at the end. So there are some tools there that you can use.
Next question.
My question is for any and all of you. I heard different potential obstacles. There was questions or doubts about structural integrity. There was maybe hesitance by contractors for using the material. There was a statement about it being done outside of California, but not in California. So I'm just hearing different maybe blocking points, and my question is, what are the major obstacles to more widespread use, in your view?
Well, I'll just say it's just familiarity, right? Anything new is can be potentially scary, especially when you're talking about from a contractor's perspective of compliance and cost, right? And then what type of equipment they need. But what we found in both cases, we've done 2 different projects with TDA, and once the contractor's in there and we are verifying with them that they're doing it the right way, and yes, it feels weird. Like you walk on that, it's moving, it's bending, it's flexing, and it doesn't feel like it's compacting. So when the contractor's out there, it doesn't feel right. And we just keep telling them, you're doing it right, it's gonna work, just keep going, just follow the method. And when we get to the final grades where we're putting in our granular fill, then we'll start taking compaction, and you'll see that it's verified. We're getting 95% compaction in the fill material above it. You can't do that with something that's not compacted underneath. Right.
The question is about the approval process. I mean, you're the City of Public Work, so I'm living in a different city, and I'd like to get approved by the city. Do I go to Public Work, or how do I get an approval to do a project like this?
Well, I guess in my case, we are the agency, right? And this is a pilot project, and we understood that there are risks, but there are rewards. And we were looking to solve a problem, so I took the lead in working with our agencies, and it helps to have support from people to venture forth in a different direction than is traditional. Some agencies are more likely to do that, especially on a smaller scale, a specific project. Maybe not for widespread use, but there's specific areas that this is a beneficial product. But yeah, it takes initiative, I guess.
Yeah, I was going to respond to the last question, kind of with the same thing, that since we're a separate state agency who's constructing a light rail line for turnover to, in our case, LA County Metro to operate, our biggest challenge with our first project, 2012 to 2016 project, was getting Metro's in-house engineering staff comfortable with it. So in 2010, 2011, as we were planning and doing preliminary engineering for that project, we had to do a lot of modeling, a lot of discussion with their structural engineers to convince them that it was going to be just fine. And lo and behold, it was.
Chris, another question was, the particles on the film, or from what I could see, they looked pretty big. What size did you use? And also, did you guys ever experiment with like how they would interlock with maybe a larger size with the smaller size in there for compaction at all? Just curious.
We use the type B TDA, which is the larger diameter TDA. And for us, it has, I think, a better ability to have more tensile strength, which is what we were looking for. And then the tensile strength interacts with the geogrid that we're using, right? So it provides a pretty good resistive force for those supportive elements in there. So it was the right material. And we didn't really want to fill in the voids, right? Because filling in the voids is basically just reducing, or it's increasing your density of the material, which is more weight. So having the voids in there is actually a really good thing because it's reducing the weight on the underlying materials. And great permeability too, right? It allows any water that accumulates, in this case from the adjacent areas, to be able to transmit through readily.
Yeah, and type B TDA is pretty well graded. It's definitely not uniform. You're not having all the pieces like at 1 foot. You're getting some smaller pieces. So I think you do get pretty good interaction. When we were taking apart that big 10-foot box, we took the front face off and it stood vertically. So if you had that filled with sand, it would all slough out. So TDA is a very interesting material. It has very good interlocking, and yeah.
Any other questions in the room? Do we have any virtual questions? No? Okay. Dr. McCartney, I want to thank you again for joining us all the way from Croatia, and I want to thank all the other presenters.
Sorry, Matt, sorry. We just got one.
Okay.
First
Question to
online
Dr.
question.
McCartney. In a future potential application to building.
Yeah. Do you
or
want me to
bridge.
read it out, or can you?
Sorry?
Should I read the question out to the audience?
John, can you see the question?
Yep.
Okay, go for
Yes,
it.
go ahead.
The question is, in a future potential application to building or bridge shallow foundations, are there concerns regarding TDA material degradation or aging during their life cycle? Additionally, if TDA below the foundation needs to be replaced or retrofitted later, what kind of strategies can be considered? I mean, in my experience, one of the good things about this burrito wrap is that it keeps the TDA isolated from the environment. And the rubber material has, I think, very good degradation properties. I think there's been several long-term TDA projects that have been going on for 30 years, and I don't think people have observed problems. But one nice thing is if you do need to replace it, it's encapsulated, so you just dig down to where it is and remove the geogrid. But we use a lot of different polymers in landfill design as well, and geotechnical engineering, and all of those polymers are rated to last for 50 years or more. So I think you can count on TDA to also last that long. Hopefully that's,
All right. Any other questions?
I think Joaquin is familiar with some more studies that have been performed by CalRecycle as well.
Okay, and I think that will conclude it for our presenters and our session. So thank you again for attending and participating in this session. Submitted presentations are posted in PDF format on the conference agenda page. And without further ado, I'll hand it back to our MC, Kyle Pogue, to transition us to the next session. Thank you.